This is a 1 capacitor crystal radio, and it works pretty well. The selectivity is good, but the sensitivity is a little weaker than, say, the wiper style crystal radios. And I read somewhere that if you want a more efficient coil, you have to have a bigger coil. So I've got radios that have a 2-inch coil. This is a 1.5, and that's what a 2-inch looks like in comparison. My current favorite radio, because of selectivity and sensitivity, is this dual wiper, and it's got a 3-inch, and you can see the difference in the coil size. I mean, it's huge in comparison. So the question is, will that continue if I keep making the coil bigger? And to that end, I went out and bought this thing, which I can't get on all on the camera at one time. This is, what do they call it? It's for sewing. And yeah, you put a piece of cloth in here, and it's got 2 rings. You clamp the cloth down, and then you can sew on it. But what I plan to do is use the inner ring to wind a coil, put the wire around there, and then clamp it and use that for my coil. Now, yeah, you're kind of saying, well, how does that work? Well, the orientation will be like this. Yeah, so the coil is going this way. It's going to be really short this direction and really tall that direction. And if it works, I mean, you know, if it scales up, so if bigger is truly better, then it should have some interesting results. Right now I am struggling with how to wind the wire on this because it's only 1 centimeter, about 1/2 inch wide. Wire doesn't like to stay on there, it pops off. In the ideal world, I would cut a groove on the outside of this inner ring like that. I would cut a groove in there that is 6 millimeters wide, and then I would wrap my wire within that. I've thought about all sorts of things like double sticky tape, but that's just not a permanent solution. Double sticky tape comes loose over time. Yeah, so if I'm going to go to all this trouble, I want to make sure it's, you know, it's like going to be around for 50 years or, you know, something grandkids can have. Okay, so how did I come up with this? Well, I guess the next step is we should go over kind of the design and the logic behind this and see where it came out of. Some notes from my future self. Yeah, I made some assumptions, some mistakes happened as a result, and hopefully I've learned some lessons, hopefully. Okay, let's talk about the design and some calculations that went into this. The hoop coil is 36 centimeters or 360 millimeters in diameter. We can see this inductor tool over here that I used. This is from ElectroDock. It's an app from the phone. And I put in 18 turns of 0.22 millimeter, and that's somewhere between 31 and 32 American wire gauge. So the coil height, this H, is calculated by 0.22 times 18 turns, and that gives me 3.96 millimeters. And the overall inductance is about 250 microhenries. And we need a resonant range that includes 540 to 1600 kilohertz, the AM radio band. So to get that range, we start with our inductor of 249, so that's over here. And by the way, these are the icons for the apps I'm using. And so we start with 249 microhenries and 36 picofarads, because that's the bottom end of my variable cap. And that resonates at 1681. That's kilohertz, and over here it's listed in megahertz, so it's 1.681. And here, then, the top end of my variable cap is 365 picofarads. And we plug that in here, and we end up with 527 kilohertz. And yeah, that's within the AM radio band. So this the calculations work out. Now we are going to have to scale that. So this is the original design. The important thing is this coil, obviously. So there's 20 turns for this antenna ground circuit. There's an additional 30 turns here for the headphones, and then there's another additional 80 turns, and this coupled with the headphone circuit makes up the tank circuit. So that's the resonant circuit part. Okay, so let's look at the ratio logic, and we start out with the original air core, so that's what I'm calling this one. And the total turns are 80 plus 30 plus 20, which gives me 130. And I've measured this at 205 microhenries. Actually, I measured from here to here, so that should be, the 205 is at 110 turns. I should have put that down here. Okay, so the tank turns are 110. Again, that's from here to here. And the earphones are 30, and the antenna is 20. So now we need to scale that up to our hoop, which instead of being about 2 inches in diameter is 36 centimeters, or almost a foot in diameter. We have start out with 110 turns from here to here, and we need to scale that to this point from here to here. And I just did a simple ratio of 110 to 18 turns, and I'll show you how I got that in a second. And that equals 6.111 turns for every one of these turns. So 20 divided by 6.111, 30 divided by 6.111, and 80 divided by 6.111, and that's where we're going with this. So the total turns, 3 for the antenna plus 18 for the earphone, that equals 21, and that's across there. Tank turns, so 5 and 13 is 18. Earphones are 4.9, so I rounded that to 5. And then the antenna is 3.3, and I rounded that down to 3. So the summary is 21 turns, and I'm going to tap at 3 and 8 turns. So tap there and tap there, so that's 3 plus 5 is 8. Okay. The physical hoop is the windings, so I take 0.22 millimeters times 21 turns, and that gives me a coil height of 4.62 millimeters. Or most of the time we look at the coil laying on its side, so it'll be, you know, the length sideways, 4.62 millimeters. The best I can do is if I could cut a channel in the hoop and then lay the wire in there. The next best choice is a double-sided tape about every 3 centimeters, and then cover the whole thing with white glue. Okay, from my future self, I came back and told me what my results were, and I got a measured result of 257 microhenries, which, you know, that's pretty close. Yeah, that's definitely workable. And if I put that in the calculator and use the 36 picofarads, I get 1655 kilohertz. So that's within our range. And the 257 microhenries with 365 picofarads, 519. So, okay, we are within our range in the final result, in the actual result. And I ended up using two-sided tape because there was no way I could figure out how to cut a channel in the hoop without destroying it. Okay, yeah, surprise. I thought, you know, while I'm doing this, I might as well just make a Litz wire version of it, right? So, surprise, this was not in the original plan, but here it is. Same design, same everything, except we're going to substitute Litz wire. And the second hoop I ordered, I got a smaller one because the first one was kind of big. So I got a 30 centimeter hoop, or actually, you know, 31 centimeter hoop when I actually measured it. So the plan turns out that I use 19 turns of 0.26 millimeter. This is again Litz wire, so it's 30 American wire gauge wire. And the coil height, again over here, is 0.26 times 19 turns, and that gives me 4.94 millimeters as far as that goes, so that's where that comes from. The inductance works out right there to 235 microhenries. And again, this is per the ElectroDock app. That's what it looks like. That's actually a screenshot of it. Now, here's a note from future self. ElectroDock is for single strand copper. So yeah, this is a hint that something's going to happen. Again, we need that same range, 540 kilohertz to 1600 kilohertz to get our AM band. And let's do our calculations. Again, we need to stay in this range, and we're going to get this for our inductance. That's the calculated. So we're going to plug it in over here. We got 235 microhenries, and we use 36 picofarads, and we get 1.7 megahertz. Then we plug in 365, and 365 is there, keeping this the same, and we end up with 542 kilohertz. Again, it's very close to our range. We need just slightly more capacitance to get down to 540 kilohertz. Most of the variable capacitors will have a little tuner on them, so you can do that to add a little bit of capacitance, and yes, we can. Okay, so again, we're going to do the ratio of turns logic. This hasn't changed at all, so I won't cover that again. But we're going to go down here, and we have 110 compared to 19 turns. So instead of 6.111 turns per one turn, we're going to end up with a ratio of 5.789, or basically 5.8. So the numbers over here work out to 3.5, 4.5, and 14 turns. So each one of those in the different sections. That gives us a total of 22.5, and the tank turns will be a total of 19. Oops, that doesn't match, does it? Yeah, that's one of those things that's coming up to bite me. Future self has come back and told me. So earphones, 5.18 rounded to 4.5. Yeah, I did this on the fly because I made a mistake in thinking. Fortunately, there's going to be a little bit of luck here, and that error in thinking is actually going to help me. Okay, antenna to ground, 3.5. I'm not going to round it. So this means that this is going to go 3 times around the hoop and then half turn more. So that means that this lead right there, the ground lead, is going to be on the opposite side of the hoop. So 22 turns total, tap at 3.5 and 8. Well, yeah, future self has fixed me. So once again, I wanted to cut a channel in the hoop. Not going to happen, and I would need a channel that's about 5 millimeters wide because of just taking the multiple of the wire. So I ended up using the 2-sided tape. Yeah, and here are the actual results. The tank is 18.5, so that plus that. I measured it at 289 microhenries, and oopsie doodle, because with 36 picofarads, that puts us outside of the, it puts us below what we need. So we need 1600, and we're getting 1560. And then with 365, yeah, we're plenty low for the low end of the AM range, but yeah, so yeah, this is whatever, not good. So at about 16 microhenries per turn, I have to remove about 2 turns to get down to 250. And again, that's based on actual. So you see what's happening here is the applications work fine for single strand copper, but when it came to the Litz wire, it's a good estimate, but it's not quite working right. The Litz wire is apparently more efficient. So when I actually measure this, I get about 49 microhenries more than I need. Okay, so the accident of rounding down from 5 to 4.5, yeah, that actually helped things. So I was lucky that I did something that really was kind of dumb. I really should have rounded this up to 5.5, but that would have made it a lot worse. So again, sometimes, I'd rather be lucky than good. Okay, so note down here, the single strand resonance calculator does not seem to be accurate with Litz wire. I have finished winding the coil, and frankly, it was one of the hardest things I've ever done as far as crystal radios go. I won't do another one until the second one I'm planning. Yeah, there's a little bit of a spoiler, but I've got my taps in here. So this is the antenna, this is the ground, this is the first part of the we call it earphone circuit, and then this is the other end of the coil. And then you can see the copper over here, it's wound around there. What I did is I made marks, and they're hard to see now, but I wanted to center this as much as possible, and so I made pencil marks around here about 2 or 3 millimeters from the edge all the way around. And finally I decided the only way I could do this was to put, what do they call it, double-sided tape. About every, well, you can see them here. There's a set, there's a set, there's a set, there's a set like that, and all the way around here. And I laid it on there, and yeah, it liked to pop off. It liked to do everything until you get the first 3 turns on here. It's just absolutely, you know, horrendous. Just the wire just wants to keep coming off. So yeah, really difficult thing to do. Let's see, what else would you want to know? So the double-sided tape, the black tape is on here after I got done. I put it on here to keep it from just destabilizing, whatever. Then I coated it with white glue, and you can't really see that, but it's, yeah, it's dried now. What else? What other construction note? Yeah, that's about it for that. I will put this over the outside. So these sewing hoops, they come in pairs. One's a little bigger than the other. I will remove this metal work on here and probably replace it with some strings. It's got some little pop rivets, or not, whatever they are, kind of rivets right here. I'll drill those out, and then I'll just use string across here and use this to protect the coil and also make the antenna a little stiffer overall. How am I going to mount this? Well, right now I'm thinking about using one of my old tricks where I will glue it to a board like this, and then for extra strength I will drill some holes in the board and then wrap it with thread and glue, and that's usually pretty strong. And then of course I'll screw that to the base, which is hiding over here. And yeah, it'll replace this coil right here. So this big coil will replace this little coil, and that'll be it. So that's next thing to do is what I just described. I need to get this thing onto here, get it onto a board, get it mounted, and then we can actually apply it here to the base of the radio. I almost forgot to mention that while I was winding this, I was trying to watch TV, and I wound too many, I lost count of the turns, and I put too many turns on here, and when I put it on my inductance meter, which is a good thing I had, it was too much. And what I had tried to do is I just jumpered it onto the base here and was listening to it. It sounded like reverb, and I'm like, yeah, something's wrong. So that's when I used the meter, found out I've got almost twice the inductance that I needed, and then I had to sit here and peel off turns, and they were about 50 microhenries per turn as I peel it off. So that means I got about four turns too many. So yeah, you really have to focus while you're doing this. And again, like I said, it's a hard thing to do, and the focusing was not fun, but the next one I do it's probably going to be the last one I do, but yeah, I really need to keep track of it and not let your attention wander. I just looked at the other video clips, and I realized that I left out some important construction notes. So before I go on, let me go over that. You can see these fine wires, and they are inside, or they come through the wood is the best way to say that. They cross over and they go over to here where they attach to a bigger wire. Now let me show you a little bit more about that. So what's going on is you can see these marks here, and that's where I put the first winding on it, and that winding emerges from that hole right there, and it starts around, and on the other coil, on the bigger coil, this would have been the ground right there where I have the X, but as the calculations on this smaller hoop work out, the tap will be on the far side over here. So, okay, back to this. So we have 1, 2, 3 holes. This is the start hole right here. This one would be, again, it would be the ground, but it's not going to be there. It's going to be on the other side. This would be the other side of the earphone, and this would be the end of the coil. And you may be able to barely see some holes here, here, here. So what's going on there is that I run the fine wire from here over to something a little bit more robust, which is this metal pin. And it's just a lead that I cut off of a, you know, like a resistor or something like that. And drilled a smaller hole on this side and pushed this in there. Then I will solder the smaller wire onto here and the bigger wire onto here, so it gives it some kind of a strain relief. And when I'm done with that, I put a little super glue around the base and then shrink wrap it. So those are the things I missed telling you the first time. I thought we would compare the original air core radio, which is this one, and then this, which has been modeled after this radio. It's got the same style of windings back here, but of course on a different core. It's hard to see this back here, but if I zoom out, then you can't really see the scope. But what we're going to do is we're going to compare these two things, and I've got one of the channels of the oscilloscope. So the yellow channel is on the original, and the blue channel is over here on the new one. They're basically the same radio, so they're both tuned by capacitor. I've got the earphones here, and they're got one in each ear, and I have tuned them until they are the same loudness to me. And you can see what happens if they're not the same loudness. They break apart. So let me get them back together. And what we can see is that, well, basically, the blue one is, let's see if we can get a good shot here. There we go. The blue is typically bigger than the yellow. Let's run that, okay. So like here, not always, but on the average, the blue is about, I don't know, I would say 20% more, like this. That's pretty typical right there. And that would indicate that this radio is performing more efficiently. And why do I say that? Well, they're both using the same antenna, they're both using the same ground, so they have to be sharing that signal. So whichever one of them has the more efficient operation will grab more of the signal, if you will, assuming all things are equal. This one has a bit of a disadvantage because, as you can see, I've jumpered the hoop by, just plain old jumper wires. And this one, they're direct connect. So yeah, this one has some more connections and obviously some more resistance, but overall it is outperforming. I will be honest, I cannot hear the difference in my ears, but this one might be a little clearer, but overall, yeah, they're about the same. But the equipment's not going to lie to us. Okay, so now I thought what we would do is compare this to the Litz wire hoop. I guess I forgot to mention, this is just the plain hoop with the ordinary single strand copper. And so we'll substitute out this for the Litz wire hoop, and we will do this again and see what kind of difference we get. Okay, same setup as before. We have the original air core, and then we have the new radio with a hoop. I have swapped out the single strand copper for the Litz wire, and you can definitely tell because here's the black ground wire coming up there. Again, the same connections across the bottom otherwise. And again, the yellow tracing will be here and the blue trace will be here. And we can look and see what's going on. To me, the hoop radio is a little clearer and definitely louder. I can tune it louder. And considering they're both using the same antenna and ground, they're competing for that signal still. Yeah, it would seem to indicate that this one is the more efficient one. Now what I have to do is I have to decide which of these hoops I'm going to use, because I'm only going to build one of these radios. And I have to figure out how to mount this. I got a fair idea right now, but I got to mount it, put it on here, and make it permanent. So that's the next step. Some final construction notes. We got it all together now. This is just a thin piece of paneling that has been screwed to the back of the base, and I zip tied this in a few places. I also put the outer frame on here and I tied it in place with thread just to give it a little bit more strength and to protect the wire. I chose the Litz wire loop because Well, it just seemed to give a little bit better performance, and I suspected that once I got rid of the jumper wires, that it would give much better performance. I ended up stripping out 2 turns on this, and it came down to, I think it was 224 microhenries, which a little lower than target, but this capacitor is a little higher than target. This is more like 540 picofarads instead of the usual 365. So between the 2 of them, again, I got lucky and it works out pretty well. Here we've got the oscilloscope set up. You can see that I've got a station tuned in, and I can pick up another one over here somewhere. There it is. There it was. There it was. Yeah, there it is. And you say, well, so what? That's only 2 stations. Yeah, but if you notice, the antenna and the ground aren't hooked up. So this is so sensitive that the coil is actually acting as an antenna. It's not intended to. The coil is supposed to be a coil and nothing more. But again, the radio is so sensitive that it is picking up 2 stations with no antenna, no outside antenna. And yeah, let's see if I can get that on there. 1, 2, and you can see what it does to reception. Boom. So I got 5 stations testing. It's 5.5, call it. Let me make sure I can hear things. Tuning. There's the half station. Very faint, but there it is. Playing music, somebody's talking. Okay, there's the first loud one. Actually, there's a guy talking. And the next station over is very close. There's music. Oh yeah, you can definitely see that's a music. Woman talking, but it's being, yeah, you can still hear the other station, the music. But there's a woman talking. Man talking. And then you can see, and the song is "You Look Wonderful Tonight," and it's ending. But you can see it's just blowing the thing away. So I think there's 6 stations I'm getting, 5.5, 6 stations. So the question is, would I recommend building this? And when I first started testing it and everything was jumpered in place, I would have said no. It's there was just too much resistance with the jumpers, and I suspected that might be true. So when I completed it, I hooked it up, I was pleasantly surprised with the fact that it has very good sensitivity and very good selectivity. So yeah, would I recommend it? If you're an advanced builder, yes, I think this is very good. The Litz wire, the big coil, if you've got room to store it, this is a very good choice. So yeah, I don't know what else to say about it. The wiring is the same as before. And again, I just made it permanent instead of using jumpers. But yeah, I think this is going to be one of my favorite radios. I really like it, just first impressions. Okay, well that was it. Hope you found that useful and interesting in your radio explorations.